The purpose of this video is to show that as a consequence of the snake lemma, singular homology satisfies the long exact sequence axiom. So to prove this axiom for singular homology, let us first of all recall what this axiom said. So let me write the title, the long exact sequence axiom. And we will now denote by big H singular homology. So let H star denote singular homology. And what we have to show in order to see that the axiom is satisfied is the following. For every pair of spaces, so for every object x comma a in the category top 2, we have a natural long exact sequence. Okay, so long exact I don't need to write, we just write exact. We have a natural exact sequence of the following homology R modules. So it's infinitely long. I just write the portion starting at degree n plus 1. And there we've got the relative singular homology of x relative to a. And then from there we have this boundary homomorphism, delta n plus 1, going to hn a, then to hn x, and then we've got yet another inclusion into the pair hn x comma a, and so on and so forth. Yeah, so now there would be the next boundary homomorphism going to hn minus 1 of a. Yeah.
And just to be clear, we're not just proving the axiom, we are also completing the data that belongs to a homology theory, right? Because
Yes.
this boundary operator
Exactly. This would
is
have
not
been
yet there. Yeah.
my next remark. Yeah, we still need to construct actually this natural transformation here. Yeah. So the point is there are two concepts which mustn't be confused here. We have this notation D, this del operator. We have used it for the differential or boundary homomorphism in chain complexes, and at the same time it also denoted this natural transformation going from the relative homology here, x comma a, to, well, if you want, the inclusion from pairs of spaces to spaces first, where we just map this pair x comma a to the pair a comma empty set, and afterwards we plug in homology of one lower degree. And the natural transformation between this functor and the composition of the two functors I just mentioned, that's supposed to be a natural transformation, and this we still have to construct. We haven't seen it so far. Yeah? So far we only defined relative homology and as objects, but we didn't really see what this boundary homomorphism is. So that's sort of part of the proof now. It will come out of the proof, the construction of this natural transformation. So let me put this in Word, in writing, so that we don't forget that this is part of our task. So we still need to construct all these boundary homomorphisms. So these the natural transformations D star. Still need to construct the natural transformations D star. Okay, so far so good. So this is what we have to do today in this video, and to do so let me first collect some preliminaries. To prepare the proof. So I want to introduce some more terminology which will also be convenient for the rest of the course. So the first preliminary remark is that actually chain complexes form a category. Yeah? So we still have to talk about what morphisms of chain complexes are. But that's what we're going to do right now. So chain complexes of R modules form a category for which we should also fix some notation. So let's call this category R mod. Underline as usual, like this. And we have to discuss morphisms, and morphisms in this category are so-called chain maps. So morphisms are chain maps, so we should define what that means. Put it in green. So they look like this. We denote them again by this notation with the lower star index. And well, it now goes from one chain complex to another. I mean, of course, objects in this category R mod are just chain complexes. So one chain complex, let's denote it by C star with corresponding boundary homomorphism D star index C to distinguish it from the other one. And the other chain complex we denote it by D star with boundary homomorphism DD star. Okay, and what is such a homomorphism? Well, it's a family of homomorphisms of R modules. So that is families of R module homomorphisms which gives sort of a commutative ladder of chain complexes, so that you have two rows, the chain complexes, and these family of homomorphisms are vertical maps between these two rows of chain complexes. So let's put this down. These are families of R module homomorphisms, so each one is one such R module homomorphism, going from C star to D star. Yeah, so you can plug in now any n here into the star. And the requirement is that the following equation is satisfied such that DD star after F star is the same as F star minus 1 after DC star. Yeah? So this is precisely asserting the commutativities of the squares in the ladder. So maybe better than this formula is a little diagram. Let's write it down. So we here got our chain complex C, so Cn plus 1 going by D Cn plus 1 to Cn. Then we've got D Cn going to Cn minus 1, and so on. And the same thing down here with D's instead of C's. Going to dn minus 1 and so on and so forth. And here we've got ddn. And now a chain map means I've got these vertical maps here. Yeah? So here I've got fn plus 1. And here I've got fn. And finally here I've got fn minus 1. Yeah, and the equation you see here asserts precisely that all these squares here commute. Yeah, going this in this order is the same as going in this order. Okay, so these are the morphisms in the category. And now let me recall, more or less, a remark that I had already made earlier. In the definition of singular homology, the construction was that we first came up with a chain complex, and afterwards we took the homology of the chain complex, and this defined the singular homology functor. And of course, the second part is just an algebraic construction. So actually, homology is a functor from the category of R chain complexes to the category of R modules. Yeah, this is the remark. Homology is a functor. Homology is a functor called Hn, going from the category of chain complexes to the category of R modules. Of course, the important part of a functor is that it's defined on morphisms. So what this says is a chain map, as just defined, gives an induced map in homology. Yeah? So this map F we had up there would give a homomorphism of R modules from the nth homology in of the chain complex C star to the nth homology of the chain complex D star. Yeah? So we get induced homomorphisms in homology in all degrees. Okay. Next preliminary remark is that we can also define the notion of a short exact sequence of chain complexes. So that's another definition. A short exact sequence of chain complexes which we denote like this. So going from 0 to 1 chain complex, say A star, then we've got a chain map of chain complexes to another chain complex B star, and we've got another chain map G star to a chain complex C star. So first of all, a short exact sequence of chain complexes is of course such a sequence of two consecutive chain maps, and this condition that it's supposed to be a short exact sequence now just means that whenever you plug in 1 degree, you really get a short exact sequence of R modules in the usual sense, as we knew before. So a short exact sequence of chain complexes is a sequence of chain maps like F star and G star giving short exact sequences of R modules in every degree. Giving short exact sequences of R modules in each degree. Yeah. So if you want, you can picture it like this. You can sort of think of that the differentials of the chain complexes now go vertically. So you sort of get the chain complex like listed up vertically. And in each degree, you've got now maps in the horizontal direction, so that in total you get a whole plane diagram, yeah? But all the rows are short exact sequences. This is the complete picture of what a short exact sequence of chain complexes is.
And one can argue with short exact sequences of chain complexes in the same way as for short exact sequences of modules. So in some sense, all these conclusions are very similar, and the sophisticated reason for that is that both chain complexes and modules form abelian categories.
Yes.
But to make it concrete, so for example, we had this fact that we used in the long exact sequence, that if you have a short exact sequence of R modules and this sequence splits, for example, there is a map from C to B that splits the map G, then B is the direct sum of A and C. And that holds exactly in the same way for chain complexes. So if you have now a chain map from C star to B star, such that the composition with G, so
in this direction,
in that direction, and then followed by G is the identity on C star. If you have such a split, then you have a split at the other position, and B star is the direct sum of the chain complexes A star and C star.
Yeah, and direct sum would now be the co-product in the category of our chain complexes. So actually, yes, one can sort of denote or formulate all this categorically, even what kernel and image is. There's a categorical formulation for this, so that one can make sense of exactness in abelian categories, but this is not the path we want to go down right now, right? It's just a remark. So for us, the exactness means the usual algebraic exactness in each degree. Yeah. Okay, so this is enough of preliminaries. So we now formulate the theorem we want to prove. And the assertion is that whenever you've got a short exact sequence of chain complexes, you obtain an associated natural long exact sequence of homology groups. So let us give ourselves such a short exact sequence of chain complexes. C star, D star, E star. Let this be a short exact sequence. And now I use the abbreviation short exact sequence of chain complexes, or in other words, a short exact sequence in this category, as Roman just said. So let me write a short exact sequence in R chain. Sorry. Then the assertion of the theorem is that we obtain an associated long, exact, and natural sequence. So then we obtain a natural, long, exact sequence of homology groups. So this now goes like this. From Hn plus 1 of the last chain complex star there, E star. And then we get a connecting homomorphism. So again, construction of this homomorphism is part of the assertion of the theorem. Going to the nth homology of C star. From there we go to the nth homology of D star. And from there we go to the nth homology of E star. And afterwards the pattern repeats. Yeah, so it goes on and on and on. Okay. So this is the main theorem we got to prove, and we'll see afterwards that as an immediate application of this theorem, the long exact sequence axiom for singular homology will come out. All right, so let's prove this theorem. And as promised, this theorem will actually be a pretty immediate consequence of the snake lemma. So we need to come up with a diagram to which we can apply the snake lemma. That's sort of the first step. And this comes out of these chain maps pretty easily. So what we do is we apply the snake lemma to the following diagram. So just the following portion of this short exact sequence of chain complexes where we just start at degree n plus 1. So here we've got Cn plus 1, here we've got Dn plus 1, and here we've got En plus 1. Yeah, so this is the short exact sequence one obtains if one plugs in the degree n plus 1. And we just go down one step here, right? So now we've got Cn here, Dn here, and En here. And the morphisms going down here, these are just the differentials, right? So this is the differential in C and n plus 1. Actually, I'm not sure if I ever said that a different word for boundary homomorphism is differential. I say it all the time. Yeah, it's just completely synonymous words. So here we've got the differential of the chain complex D. And here we've got the differential of the chain complex E. Okay, and the requirement was that we had a short exact sequence of chain complexes, which means here the horizontal lines are exact sequences. And as we saw last time, this is precisely the kind of diagram to which the snake lemma applies. And what does it give us now? Well, it gives us a 6-term exact sequence, of which we only need the last 3 terms. So by the snake lemma, we obtain from this an exact sequence from this co-kernel. Oh, maybe I should leave it visible, I'm sorry. So from the co-kernel of this very map here, so Cn modulo the image of dCn plus 1. From there going to the co-kernel of this boundary homomorphism here, so that's Dn modulo the image of the D differential, ddn plus 1. And from there we've got the co-kernel of the last differential, so that's En modulo the image of dE n plus 1. Okay, and part of the statement of the snake lemma was also if we've got this diagram which really has all 4 zeros here, then the last map here is also surjective. So actually we get an exact sequence of this type here. Okay, so that was the first application of the snake lemma. And now comes a second application. We just repeat the same process for the portion of the chain map of this short exact sequence of chain complexes for 2 degrees lower. So now we apply the lemma to the following diagram. where we now start at n minus 1 instead of n plus 1. So let me write it again. 0, Cn minus 1, Dn minus 1, En minus 1 to 0. And then we've got our differentials going to Cn minus 2, Dn minus 2, and En minus 2. Yeah, and these vertical maps are again the boundary homomorphisms. Okay, so applying it to this diagram, we obtain again a 6-term exact sequence, but this time the relevant portion of it are the first 3 terms, yeah, which were the kernels of these maps here. Yeah, so it was, I mean, if you remember, the snake lemma said that we know the exact sequence starts at the kernel of this map and goes to the kernel of this map and then to the kernel of this map. And let's now recall what these maps here are. Well, this is just the differential in n minus 1, and we had already introduced terminology of what the kernel of such a differential is. We called it the cycles in the chain complex. Yeah. So let me also write it down like this. So what we get from this is this time an exact sequence starting in 0, and afterwards we get the n minus 1 cycles in the chain complex C star. And from there we go to the n minus 1 cycles in D star to the n minus 1 cycles in E star. Yeah, where again, this is just different notation for saying it's the kernel of the n minus first differential. Okay, so far so good. So now we have 2 portions of exact sequences, and guess what? These 2 exact sequences stick together to give yet another diagram to which we again can apply the snake lemma. And this is the next step. So we obtain the following diagram. We start with the first portion. This was the co-kernel, Cn image Dn plus 1c. Going, I mean, maybe I can actually copy it. I think rewriting it is faster. So Dn image Dn plus 1, and from there going to En to the image of Den plus 1. And there it went on 1 step further to 0. So this is an exact sequence. And so now we've got these 2 exact sequences. This came from the first application of the snake lemma. This one came from the second application of the snake lemma. And now, as we come to think about it, actually we also got vertical maps here in this diagram. Because now here we just put, whoops.
You have to change the pen.
I have to change the, yeah. I just put here the arrow, which is the induced one from the nth differential in the chain complex C. Yeah? So Dnc is defined on Cn, but as we already proved, the composition of 2 differentials is 0, which means here the submodule that's factored out is actually mapped to 0 by the differential, and therefore we obtain an induced map on this quotient here. And it does actually end up in the n minus 1 cycles, because for the same reason, if I now would apply yet another differential going down to n minus 2, this would give 0. Yeah? Because it's, again, a composition of 2 differentials. And therefore, we obtain a well-defined map dCn bar from the quotient to the cycles. And exactly the same reason applies for the other 2 horizontal maps. So this is the induced map of the nth differential in D, and this is the induced map of the nth differential in E. And as we see now, now we're again in good shape. Yeah, I mean, since those were chain maps, and remember these are induced from chain maps, so therefore these 2 squares here commute with the differentials. So we've got a commutative diagram here where both rows are exact, and it's also of the shape that we needed, that the lower one starts at 0 and the upper one ends at 0. Yeah, so this is exactly the kind of diagram to which the snake lemma applies. So we can now do yet another application of the snake lemma. And we get out of this a 6-term exact sequence, namely starting from the kernel of this map, going to the kernel of this map, going to the kernel of this map, then the connecting homomorphism, and afterwards co-kernel of this map, co-kernel of this map, co-kernel of this map. Yeah? So let me write this down. We get kernel of dnc to kernel of ddn, then we get kernel of den, and afterwards we've got this connecting homomorphism which we denoted by delta, and from there we go on to the co-kernel of dcn, and then the sequence continues, going to the co-kernel of dnd bar, and then to the co-kernel of dne bar. And there actually it ends. Sorry, this is not an arrow in the category also. This was meant to be like an arrow saying we get out of this this exact sequence. Yeah, this had no mathematical signification. All right, so this is what we get out of this, and now I claim this is exactly what we want. Yeah. So let's see why that is true. Now the kernel of dnc bar, I claim this is just, well, it's almost philosophical if I write isomorphic or if I write equal. This is just the nth homology of the chain complex C. So why is that true? Well, what is an element in Cn, in this quotient, which maps by dnc bar to 0? Well, it means that a representative, so an element, an n-chain here, an element of Cn, must be mapped to 0 by this map dnc. But well, this means precisely that this map is sorry, never mind. What do I want to say? I want to say that this is now cycles modulo boundaries.
Exactly.
So I'm confused.
Yeah, it's the same whether you take the kernel on this boundaries or you take the kernel of the original differential and then mod out the
Yeah, so
boundaries.
what's different is the order here, yeah? We took
What's different? Yeah.
Yes, but it doesn't matter because saying that we are in the kernel of this map means we only consider, okay, I think I'm back in shape. We only consider those elements in Cn which actually do map to 0 here, and that is by definition those elements in the submodule Zn, so in the n cycles here. Yeah, okay, so this was a short confusion, but yes, the kernel of this is just plainly the same as if I had taken already the cycles, and then from this I had mod out the boundaries here, the image of dn plus 1. So therefore this is the nth homology of C star, and here for the very same reason we get the nth homology of D star, and here we've got the nth homology of E star. Then we've got the connecting boundary homomorphism, and then we should consider the co-kernel here of dnc star. So what does this now mean? This means it's the n-1 cycles here modulo the image of this map. Yes, but the image of this map, I mean, with d bar, this is precisely the same as the image of the ordinary map. So maybe I can extend this diagram here if I want. I can just write here Cn, and I've got this canonical surjective projection, and then I've got a commutative triangle in this way. Yeah, I mean, this induced map exists, yeah, because this differential dnc has the property that this submodule here is mapped to 0. So in other words, since this is commutative and this map is surjective, that means those two homomorphisms have the same image. And this means what we divide out here in the co-kernel, this is just the same as n-1 cycles, black color, modulo n-1 boundaries. And therefore, this is also just the n-1st homology of the chain complex C star. And now, let me lift this up a little. The very same argument implies that this is the n-1st homology of D star, and this is the n-1st homology of E star. Okay? So in other words, what we got out of the third application of the snake lemma is we've got a 6-term exact sequence of homology groups, yeah, from the nth homology to the n-1st homology here. Okay. So now let's discuss naturality. This is now easily done because we had the naturality statement in the snake lemma. Yeah? And this naturality statement of the snake lemma is precisely what gives naturality for this exact sequence. So let me just write that this sequence here is exact. And naturality holds by the snake lemma. Naturality by snake lemma. Actually, I was kind of confused what naturality really means in this theorem. Yeah? I mean, what it really means is that if we have a morphism of short exact sequences of chain complexes, you get a morphism of these long exact sequences. Yeah? For me, that's more like a functoriality statement, right? You've got a category of short exact sequences of chain complexes and morphisms between them, and then you've got a category of long exact sequences and morphisms between them. And I think the naturality statement just says that well, this long exact sequence construction is functorial here. But anyhow, so it's clear what it means. You get this long exact, you've got this horizontal commutative ladder of long exact sequences, and we get this out of the snake lemma here. Okay, so now we only got a 6-term exact sequence here from nth homology to n minus first homology. And what we really claim in the theorem is that we get an infinite long exact sequence. So we still have to clarify that all these 6-term sequences really match at 3 consecutive terms so that they really add up, stick together to a long exact sequence. But that actually is true because we know what these morphisms are. This came also out of the construction of the chain complex, of the snake lemma, so of the morphisms in the snake lemma. And these ones here were just induced by the chain maps, yeah? And in either case, so this is induced by the chain maps, and these lower ones are also induced by the chain maps. So if you really verify what they do on representatives, then it will just be an application of the chain map, and therefore they agree every 3 terms.
Yeah, you could, now you're pushing it away already,
sorry.
But you could complete this to commutative squares, right? These isomorphisms, which are, as you said, very canonical. No, I
Which one?
The lower one.
The lower one, okay, sorry.
The isomorphisms, which are very canonical, can be completed to...
These ones here, yeah.
Yeah, these ones. And you can complete them to squares, where on the
if
lower...
you want, yeah, I mean, this is by, you mean here, yeah?
Yeah.
Yeah, I mean, by definition, right? I mean, this arrow is this arrow. Yes.
Yeah.
Yeah.
Good. But, okay, if you want to view this isomorphism as a honest isomorphism,
yeah, okay, then yes,
it's a
okay, yes,
square with and commutes with the map induced by the chain.
Yes. Okay. Yeah.
So we have the same map at these 2 positions.
Yes. Excellent. That's an even better explanation, right? Yeah. Yeah. So we get 6-term exact sequences which always overlap at 3 terms, and really get the same morphisms as Roman just pointed out, because these are these induced homology morphisms. Okay, so let me just write this down again. The last 2 morphisms, I mean 3 terms, 3 objects means 2 morphisms. The last 2 morphisms of each 6-term sequence agree with the first 2 morphisms in the succeeding 6-term sequence, with the first 2 in the succeeding 6-term sequence. Well, since they're induced by chain maps, as we just discussed. So actually, all these portions of 6-term sequences we got, they agree and they stick together to give the long exact sequence we were aspiring to obtain. and the naturality was also given by the snake lemma, so that actually concludes the proof of the theorem. And now, finally, the long exact sequence axiom of singular homology is an immediate corollary of this theorem, but let me write it down. So, corollary, singular homology satisfies the long exact sequence axiom, and the proof is now just the following. It's applying the theorem to the following short exact sequence of chain complexes, namely the one where we first take the singular homology of the subspace A. Then we take the chain complex given by the singular homology of the whole space X. And what do we do afterwards? I mean, we want to arrive now at a short exact sequence of chain complexes. So actually there's only one thing I can do now to make this a short exact sequence of chain complexes. I need to factor out this one. So I take C sing star, whoops, X mod out C sing star A, and then it goes to 0. Yeah. So this chain complex really means that at each degree it is the quotient of R modules. Yeah. So therefore I get yet another chain complex here. And now we see that all our definitions we made previously match now perfectly, because the relative singular homology introduced in a couple of videos before was just the homology of this chain complex. Yeah? So therefore, actually, the exact sequence that's stated in the upper theorem is precisely the singular homology sequence, long exact sequence that we want. It's natural as one statement of the theorem, and yeah, the natural transformation we were supposed to construct, now we see actually came out of the snake lemma as the connecting homomorphism. Yeah? And since the snake lemma also asserted naturality for this connecting homomorphism, this really defines a natural transformation, and therefore we're done for this video.